Okay, so I'm going to go through a couple examples here. What we're working on is we're into 5.4. We're solving equations. So, but we're solving trigonometric equations. I've got a couple of examples. What I'm going to do is we're going to talk about what it means to solve again. We're going to solve each one graphically, and so what it means when we look at the graph of what we're seeing, and also algebraically. And we're going to focus on primary goal is to be able to solve equations algebraically. Okay, so we've got this first equation here, which says cos of x, cos of some unknown value equals root 3 over 2, and our job here is to solve. I wanted to remind you that solve means find the value of the unknown, like find the value of x that makes this equation true, which means the left side is the same as the right side. So it's not an identity because there's not all values of x makes this thing true. Which particular values of x make this thing true? Okay, so we're trying to figure out that like what, and if you want to look at x being an angle, like what angle do I put in there so that the cos of that angle is root 3 over 2. And so what we're going to do is solve this. So solving this right off the bat is going to say like root 3 over 2 is special to us. Root 3 over 2 is one of our exact values. And so this is saying, well, what exact angle? Like what angle is it that I can put in there for x that gives me the exact value of root 3 over 2? So as soon as I see that root 3 over 2, I start thinking about this diagram right here, this circle. All right. Now, remembering parts of this circle is that cosine is the x coordinate, is the x value, the horizontal distance on this diagram. Okay, so what I'm looking at is where is cos going to give me a positive root 3 over 2? So when I look at the diagram, I've got positive coses means positive x's. So a positive x value can exist in this quadrant here, quadrant 1, because the x value here is going to be a positive value. But cos is also going to be positive down here because of this it would share that same x value right here. Wherever that triangle would lie would have an x value on this axis. So where would the root 3 over 2 lie? Root 3 over 2 being the longer of the two values that we normally compare. Is and then with a half. Okay, so what I'm going to do is I'm going to draw a long x value and a short y value. So there's a long x value right there that meets the unit circle. And if that was root 3 over 2, what angle am I talking about right here? And you might have a guess right off the bat that this root 3 over 2 is associated, these root 3's over 2's and halves are associated with all of our pi over 6 type angles, pi over 6, 2 pi over 6, 3 pi over 6, and so on and so on and so on and so on. So root 3 over 2, we got this angle right here. This is the smaller of the two. We're talking about pi over 6. So one solution to this, the solution would be a pi over 6 angle. Cos of pi over 6 is the same as root 3 over 2. So what part of our solution would say is x is equal to pi over 6. Now, is that the only case? Is that the only angle that would give you a root 3 over 2 for cos of these angles? But notice if I flip the triangle upside down into this quadrant, down here I also have that same x value being root 3 over 2. So this value here is root 3 over 2. And so what angle am I talking about here? Well, it's the flip of this. So one way to look at it is it's minus pi over 6. But also if we count around our circle, we should get a positive value between 0 and 2 pi for this angle. So that's pi over 6, there's 2 pi over 6, there's 3 pi over 6, there's 4 pi over 6, there's 5 pi, 6 pi, 7 pi, 8 pi, 9 pi over 6, 10 pi over 6, that's 11 pi over 6 right there. 11 pi over 6. So cosine of 11 pi over 6, cosine of 11 pi over 6 also equals root 3 over 2. Okay, so these are the two angles between 0 and 2 pi that would give us root 3 over 2 in this equation. So these are the two solutions to this equation. So graphically, it looks like this. If I put in cosine of x, there's my cosine function. If I zoom in, so there's cos. And if I put in where root 3 over 2 would lie, okay, so if I go root 3 over 2, I get this, and I create this to be a vertical or a horizontal line. Then wherever this horizontal line matches this, like when these two are equal, these are I'm looking for my x value. So there's pi over 6 right there, and there's another one. There's 11 pi over 6. Notice back here, there's my minus pi over 6. Past 2 pi, right? So for those two values we listed are between 0 and 2 pi. Past 2 pi, I'm looking at now just a period plus each of these. So 2 pi plus that is that, and 2 pi plus that is. I could look out and I've got an unlimited amount of answers that have this being true, where there's an unlimited amount of angles, cos of those angles being root 3 over 2. Usually what we'll do though is we'll ask, give me in this range, like between 0 and 2 pi, give me the values that make this equation true. That's usually our standard set. Okay, so there's the graphical interpretation of the solutions to cos x equals root 3 over 2. Let's look at another example. Before we do that, we've discussed that this is our goal. By the end of class, I want you to be confident with solving these types of equations. And we're going to spend a couple days doing this. Alright, let's solve this one. So it's a little different. This says 2 sine x minus 1 equals 0, and what we want to do is solve for x. Okay, so solve for which values can I put in here so that 2 times the sine of that value, take away 1, I get 0. So I could solve this graphically. I want to solve it algebraically first. So what we want to do here is we want to get a value for sine. Like instead of isolating for 0 like it is, what we do in trigonometric equations is we isolate so that it's sine x or cos x or cosecant x all by itself and then equals some number. Because if it equals some number, then we can apply what we did on the last one. Like if maybe it's a half, we can look at it, or maybe it's root 3 over 2, we can find out those using our circles. Okay, so what I want to do is isolate for sine x here. So what I'll do is I got 2 sine x, and I'm going to add 1 to both sides, so I got this expression. Then I'm going to divide by 2 on both sides, and that will isolate my sine x, and that gives me a half. So now my equation looks like this. When is sine x equal to a half? So we're solving this equation here. And so half is also special when we talk about numbers. So if I draw my circle again, I want to figure out, well, what values for the angle give me a half? Okay, now sine is positive, so it's going to be in this quadrant here, again, because sine is my y values, and so sine is positive in this quadrant because that's when we have positive y's. It's also going to be positive in this quadrant here because that's when we have positive y's. So sine is the half value is the shorter of their two values. So I have to draw a short y value so that I have that. Now notice I'm drawing the exact same triangle I drew before. We've got sine of this angle. This is going to give me a half on the y value here. So we've just showed that that angle right there is pi over 6. So pi over 6 is a solution to this solution, or this equation also. So that's one angle that works. We want to find as many angles as we can. Sine is, we just said, positive in this quadrant over here. So I'm going to flip this triangle over here. That's also a half right there, that value. So what angle is that? Let's do our counting. If that's pi over 6, that's 2 pi over 6, there's 3 pi over 6, 4 pi over 6. Hey, this is 5 pi over 6. So 5 pi over 6 must be a solution to our equation. So between 0 and 2 pi, we've got these two solutions to this equation. Okay, so graphically, let's look at that, what that looks like. If I put in sine x, there's sine x. And if I look at when it equals a half, I look at, there's where it equals a half, and x is pi over 6 at that point. and there's the 5 pi over 6 right there. And then notice again, if I zoom right out, there's an unlimited amount of values that have this being true. So we have to make sure we talk about which range we're looking at, as the standard is between 0 and 2 pi. Okay, so that's that way. Now look at it, if I look at it in the original format, I got 2 sine x minus 1, and I want to know when that equaled 0. So here's the graph. Notice it's got a stretch of 2, it's been shifted down 1. Here's where it equals 0. So same solutions to that original function. Okay, we've got one more example to look at.